Hi everyone, my name is Alejandra Zapata Chansi. I'm from Colombia, and now I'm going to present the article named Characterization and Adjustment Model of the Cricopharyngeal Muscle Potential from the Surface Electromyographic Signals in the Swallowing Process. Here on the screen, we can see the outline of these presentations. At first, the introduction, then methodology, results, discussion, and finally, the conclusions. At first, I'm going to give a context of the research topic of this article. Neurodegenerative disease constitutes a group of conditions associated with the progressive degeneration of the nervous system. Parkinson's disease is a neurodegenerative disorder with an incidence rate between 9.1 to 13.8 per 100,000 inhabitants per year. The swallowing process occurs as a consequence of alteration of the anatomical structures or physiological mechanisms involved in the swallowing process. Cricopharyngeal muscle dysfunction is a motor disorder evidenced by a permanent contraction of the muscular structure during the swallowing. The electromyographic signal, as we can see here, electromyographic signal is an electrical manifestation of the neuromuscular activation associated with a contraction. It contains information of a strength of matter that obeys two mechanisms. One of them is the recruitment of motor units, and the second one, the increase in the firing rate of motor units. It has two principal characteristics. One of them is amplitude, which depends on muscle size and the level of activation during the measurements. In the second one is the frequency, which is around 10 to 250 hertz. The invasive electromyography is used to register action potential from a specific muscle. The insertion of the needle electrodes is a painful process, which also requires a medical supervision and surgical intervention. This procedure involves high hospital costs and a tedious recovery process for the patient. On the other hand, we have the superficial electromyography that use surface electrodes that are placed non-invasively on the skin. This technique registers action potential from muscle fiber that in the sensitive volume of the lead field. The other aspect about this technique is superficial electromyography is not considered a definitive diagnosis technique, but multiple studies say or conclude there is a simple and safe method to detect dysphagia. Because if the nerves of muscles involved in the swallowing are damaged, the signal differs from a healthy patient's recording. So, this article presents an adjustment model for non-invasively obtaining the potential generated in the cricopharyngeal muscle from the measure of the potential on the surface of the neck during the swallowing process. Here we have the section of the neck at the C5 level, and it has three input characteristics: the input, the amplitude, the fundamental frequency, and the electrical properties of the tissues. This study proposed a new approach to determine the behavior of the cricopharyngeal muscle in a healthy person and present its potential to be used in future research where the muscle function is affected by a Parkinson's disease in the swallowing process. And now, to acquire superficial electromyographic signal, we start with a conditioning stage. Here we have the block diagram of the analog conditioning implemented for this signal. At first, we have a sensor connection in which we use three surface electrodes to detect potential of the neck surface. Then an instrumentation amplifier in which we use an ID620 instrumentation amplifier, then a notch filter, an inverter amplifier, and a high-pass and low-pass filter, with both constitutes a bandpass filter. And at the end, an offset stage. In the digital condition, we use an Arduino Mega 2560 microcontroller to digitize the signal. The acquisition of the signal was performed with a sampling frequency of 1000 Hz. Digital filtering was performed using high pass and low pass with cut frequency of 10 and to 50 hertz respectively. Additionally, the signal was denoised using the wavelet function with 5 decomposition level. In the acquisition stage, was performed with 3 healthy subjects. For each, 10 signals recording with a duration of 15 seconds were performed, and for each recording, the subjects carry out 3 water swallows. In the characterization stage, as I said before, it has 2 principal characteristics. One of them is the frequency, and the frequency domain analysis using the Welch periogram was performed, which by applying the fast-Fourier transform. The fundamental frequency of the signal was determined as the frequency where the power spectral density is highest. And for the amplitude characterization, we try to find the amplitude interval in which the potential of the swallow process occur. In this part, we use the Hilbert transform using the Hilbert function. And then the moving average was calculated using the pandas rolling function. The amplitude of this signal was obtained from the difference between the upper and lower envelope. And finally, we have a modeling stage. The CAD model of the cross-section at C5 level was performed following an anatomical structure. The electrical properties were assigned to different sections of the CAD model of the volume conductor in Compton. The multiphysics model considers 2 physical interaction domains. The first one is the volume conductor was modeled by the Laplace equation to study electrical behavior of the tissues around the muscle of interest. And the second one, the cricopharyngeal muscle, which was modeled at the bioelectric source using the cable equation, as we can see in this in the screen. As a result, we could obtain a successful characterization of the signal because we could see the potential behavior in different tissues of the neck cross-section at C5 level. In frequency, we found that the fundamental frequency of the signal corresponds to 49.56, more or less 16.86 Hz on the average from the power spectral density analysis. It is observed that the highest power amplitudes are between 40 Hz and 75 Hz. In amplitude, we have 2 graphics. The first one is the envelope obtained for a signal after applying the Hilbert transform. And the second one is the envelope after performing the smoothing by moving average. Then we found that the mean maximum amplitude of a swallow in healthy subjects be 0.119, more or less 0.043 millivolts. In the model of the cricopharyngeal muscle as a bioelectric, we found different results. We found that the values of the electrical parameters of the tissues were found at a frequency at 50 Hz, corresponding to the fundamental frequency of the signal. Additionally, we can see in this graphic the distribution of conductivity in the different tissues of the model. Additionally, the blue lines correspond of the current flow line distribution in the neck section. And finally, the potential calculation in point electrodes, we could find 3 important results. First one, this graphic shows the ratio of the potential drop with respect to the potential found at the surface of cricopharyngeal muscle. We found that the best place or best location to place the electrodes for potential detection coming from the cricopharyngeal muscle in the anterior area. The potential decrease from the source to the electrode And this behavior is given by the potential drop in the different tissues. In the last one, the voltage drop of 9% from the volume source to the surface. As I said before, the frequency with the highest depolarization energy was found at 50 Hz. It is well known that the electrical parameters of the tissues depend on the frequency. For this reason, the results obtained by the simulation depend on the electrical properties of the tissues. Additionally, the non-uniform behavior in the flow line is mainly due to a phenomenon called bioimpedance, which represents the opposition of the biological tissues to the current flow. Bioimpedance has two components: the resistance, that is the opposition of the different tissues to the electric current flow, and the reactance, that is due to the insulation effect of the cell membranes, which behave as a capacitor that charge and discharge with the flow of the current. We also found that the higher potential values were found in the anterior area. This is because there is less opposition to the polarization in these tissues and consequently less voltage drop. The studies regarding the potential generated in the cricopharyngeal muscle in healthy subjects using invasive electromyography reports those average amplitudes that we can see in the screen. This result is close to the results obtained from the simulation, and it has they are in the same order of magnitude. It should be noted that there is an intrinsic error in amplitude of the acquired signals due to errors generated in the analog and digital condition. Finally, based on the results obtained, we propose, or in this study, in present study, it is possible to propose new models that allow knowing the remote state of different muscular areas using superficial electromyography that help in diagnosis of muscular dysfunction due to Parkinson's disease, as well as the design of therapeutic strategies to promote the recovery of these motor alterations. The conclusion of this article are: the simulation of a muscle as a bioelectric source using the cable equation allowed to know the distribution of the potential generated in the volume conductor. As a future work, new support strategies for the recovery of motor alteration in people with Parkinson's disease. And last one, the model proposed can be implemented in another section in the body to develop new tools to help in the diagnosis or therapy of pathologies. These are the reference of this presentation. And thank you so much. Are there any questions about this work? Thank you.